let's go on. So we're talking about localization, right? So I promised you proof of localization. For the Anderson model, right? And we started with, I think this we already proved, we started with what is called the spectral averaging, right? So we defined, so let's take, this is more general, right? But let's take A, what did I say? Bound operator on some Hilbert space. Bound self-adjoint on H Hilbert space, and we took a vector phi in the Hilbert space. Actually, it doesn't even need to be in the Hilbert space, but okay, let's do it in this setting. And we said I alpha is A plus alpha 3 phi scalar phi. Right. And we defined, what did I want to say? We had the nice formula. This is rank 1 perturbation of A, and we had the nice formula of A alpha C inverse, right? We actually, let me just define this. Applied to phi. Phi, this we called f sub alpha of z, right? And we had seen that is a simple computation. F sub alpha of z is f of z, so this is for alpha. F of z is just f sub 0 of z, divided by 1 plus alpha f of z, right? And we had seen that we have a spectral averaging, which means that, so we can, of course, this function actually associated to a measure, right? One can write that f alpha of z is equal to the integral 1 over lambda minus z d mu alpha of lambda, right? This is just a spectral measure associated to the spectrum phi and the operator A alpha. And then we have seen this, what is called the spectral averaging lemma. Which says that if you look at the integral over of d mu alpha of lambda, right? And you integrate these measures, so these are measures, and you integrate these in d lambda, right? So over the real line, sorry, in d alpha over the real line, what you get is just the Lebesgue measure, d lambda. This is the spectral averaging lemma. Okay, so this we already have proved, and now we're going to connect this, okay, through what is called the Arnheim-Donahue theory. We are going to study actually the singular continuous, absolutely continuous, and pure point parts of mu alpha. So this is trying to spell the names correctly. So this goes back to the 50s. And I state this theorem that I will not prove. I'll give you a reference where to find it, right? But I will not prove it directly. I'll just give you a few hints on how to prove it, or the relationships. So what we do is the following. It is actually a theorem about measures. So what you can do is you can start with a measure, d mu, let's say probability measure. And you can define from this d mu alpha, for alpha a real thing, in the following way. You just do the following. You take the Borel transform of the measure. So from d mu you construct f, right, in this way. Actually, from d mu you construct f in this way for alpha equals 0, right? And then from f you construct, so this is via formula star, so So this is star for alpha equals 0. Then you use double star, this formula. This gives you f alpha, right? And you can check that this again gives you a Stieltjes transform of some measure. And you use star again. So this is double star, and this is star. Right? In this way, you can associate two. You start with a measure, just probability measure. Right? And you can start with this measure, you construct f. From f, you construct f alpha using this, by this formula. Right? And then you can come back to a measure d mu alpha. Okay? And in this way, you construct d mu alpha from d mu, completely generally. Right? You don't need any operator theoretic thing. What you need to check, of course, is that the measure that you constructed here is again a probability measure. Right? Once you, so this is clear what it is. You get a nice function f, which is holomorphic on the essentially on the complex plane minus the support of d mu. Right? So d mu is one measure on R, right? I didn't write it, but it's on R. And now we need to check that what you construct here is again, so it's going to be, this thing is now going to be a nice function, right? Which will, the f alpha, which will be holomorphic outside the real axis, that's for sure. It's easily checked using this formula, right? You can look at where its imaginary, what is the size of its imaginary part. You're going to see that its imaginary part is going to be of the same size as the imaginary part, the same sign, sorry, as the imaginary part of f on the upper half plane and on the lower half plane, right? You can look at its asymptotics using this. You look at its asymptotics when z goes to plus I infinity and minus I infinity. They will be the same as f. And from this, you can show that it is actually the Borel's transform of some measure, right, which happens to be a probability measure just by the asymptotics, by computing the asymptotics when the imaginary part of z goes to infinity, right? Because this is roughly what tells you what is the total mass of your measure, right? When you let z go to I infinity or minus I infinity, you get the total mass of the measure, right? And so you construct this. This again is a probability measure. Right? Okay. This is the probability measure. And you can construct this, but actually, not really sure. So you see that you in this way you completely remove the operator side, right? Or you show the fact that what you have as operators is equivalent to just statements about measures. Okay. And now, what we're going to do with the theorem is the following. I think it's around 58 or something. For alpha non-vanishing, we define the following set. So what's the first one? This is S alpha is the set of reals such that if you look at f of x plus I0, right, so you take the limit when you approach the reals from the upper half plane, this is infinite, but g of x is also infinite. So what is g? I forgot to define. G of x is the integral of d mu x minus y d mu, right? Squared, sorry. So this, you're integrating a positive function against the probability measure. This integral always exists. It can be plus infinity, right? It's a positive number, but it's, of course, it's not necessarily a real number. It can be plus infinity. So I'm defining the set S alpha. So for alpha non-zero, I define the set S alpha is the set when the limit, when you go to, sorry, this is, it's, I forgot the, not this, it's 1 over alpha, not plus infinity. This one is plus infinity, but this is 1 over alpha. Hope I have the right sign.
Minus 1 over alpha.
It's minus 1 over alpha. Let me check. Depends on what it is here. If I do this, then on the, if the imaginary part is positive, it should be also, if the imaginary part, yeah, right, it's minus 1 over alpha. Okay, that's fine. Really good. minus 1 over alpha. Then P of alpha is the x in R such that f of x plus I0 is again minus 1 over alpha, but now g of x is finite. Right? And L is the x in R such that the imaginary part of x plus I0 is different from 0. This is not real. Okay, so I define these three sets. And then we have the following thing. Then, if you look at the sets S alpha, alpha different from 0, P alpha, alpha different from 0, and L are mutually disjoint. And so here in these collections, I take any alpha, right? So if you take any two sets in there, they're disjoint. This is clear by the definitions. If you take now P alpha, well, P alpha is the support, or it's the essential support. Or it's this, actually, is is the P alpha, yeah, is the set of eigenvalues, is the set of eigenvalues. So yeah, just one thing, yeah, this way I need one assumption of A alpha, right? In fact, one has that what did I call it? D mu alpha pure point. So the pure point part of this measure is the sum over what? Over the xn in P alpha, and you have 1 over alpha squared g of xn delta xn. Maybe you can sign this thing, but that's fine. Okay. 3. You have that d mu alpha AC is supported in L, actually, is supported in L, right? So the absolutely continuous part of this measure is actually has support in L. And the singular continuous part is supported in S alpha. And last thing, which is clear from the first one actually, is that d mu alpha SC and d mu beta SC are mutually singular for alpha different from beta. Right. So again, here what does this mean? Right? It means that if you take d mu alpha, the AC part of this is 0. Right? It's just a definition of what it means to be supported in this set. And if you look at the total mass that's put outside of this set, it's just mass 0. Okay? D mu alpha AC is a positive measure. Okay, so I will not prove this, I will use it. I just want to make one comment actually, which is the following thing. What's the relationship between so the proof, for the proof, You can, for example, look up the book by Simon. Trace Ideas. There is a new edition, I think 2007 or so. And it's published by the American Mathematical Society. Okay. So the comment I wanted to make, just to make the connection between the mu alpha and the S alpha, right? The comment I want to make is just this. So what's the relationship between things? So the first thing I want to do is I want to, if I compute, so comment. So if I look at f of x plus iy, right, of course this is the integral of 1 over, go put an alpha here, mu alpha, lambda minus x plus iy. So if I look at the imaginary part of f alpha x plus iy, what do I see? I see that this is equal to y integral 1 over lambda minus x squared. Let me just change the notations for the moment to make psi epsilon. So this is psi epsilon. Epsilon squared, and here you have x minus y, d mu alpha y, okay? So that's a direct computation, right? So what I see is what I see is the following. So the first thing, what I see is that we have obviously f alpha. Yeah, one thing we have is that if we look at 1 over x minus y d mu alpha y, this is certainly bounded from above by g of x, right? Right. So this is just Cauchy-Schwarz, for example, because the mu is a probability measure. Right. Otherwise, if it would be a general finite mass measure, you'd have a constant. That's fine. Okay. And in particular, to say that g of x is, so this implies that, so this implies that g of x finite, right, implies that the limit of f alpha, sorry, there is no g, right? So I did do it with, this is clear with it. I take alpha equals 0 there. X plus I epsilon, when epsilon goes to 0, exists. Sorry, it's not this, it is here. I forgot the square root, I think. right? If I take Cauchy-Schwarz, I get a square root, right? I square this and square 1, I use the probability measure. The square root. And the other thing is that one sees also, so moreover one always has that, correct? One always has that if you look at epsilon, imaginary part of f of x plus I epsilon. So this by monotone convergence, this converges to g of x when epsilon goes to, right? This is by monotone convergence. Right? Because when you compute this, you see multiply by epsilon, multiply this by epsilon, put the epsilon square down there. Right? So you see that the convergence is monotone. Increasing, right? And the limit is, of course, pointwise, is exactly 1 over x minus 1 squared.
And there the limit is also when epsilon goes to 0.
Oh, yeah, sure. So when epsilon goes to 0. Definitely, it's the same thing. Of course, thanks. Of course. Yeah. So by monotone convergence, you have this, right? And what the other thing that you see is that if same computation shows that if j of x is finite, then you actually have that limit of epsilon f of x plus I epsilon minus f of x plus I 0, right? When epsilon goes to 0 plus, this is g of x. You can actually do a Taylor expansion, right? You can expand this in epsilon. Sorry, this is not this. This is I epsilon inverse. And these are the basic facts that I use actually, right, to prove this. For example, if you look at this formula, right, and you want to know where the singular part of f alpha is, right, you want to know where the singular part of mu alpha is, of d mu alpha is, and you look at this formula, you see that what you need is that the denominator has a problem, right, the denominator blows up. So you see that you are going to hit the set of points where f of x, right, the limit of f of x, is going to be, meaning f of x plus I0, where did I put it? Here it is going to be equal to minus 1 over alpha, right? And then you use the Taylor expansion that you have here, right, to compute exactly what the limit is in the case you want to look for the pure point part. Right? And you do the same thing for the singular part, and well, what's left over is the AC part. Right? Because the L is just complementary of all that you have removed before. Okay? So if you do not belong to any of the P alpha nor any of the S alpha, you belong to L. Okay. So, and from this, and the spectral averaging, and that's a result by Simon and Wolf, one has the following criterion for. You can apply this, yeah, for now. You can use this now for our Anderson model. How? In the following way. You can use this for the Anderson model in the following way. So, remember, we looked at h omega is minus Laplacian plus v omega, where v omega at u at n is just omega n un, and I assume that the omega n are iid. Right? I assume that the omega n are iid. And then what you can look at is the following. You can write omega h omega, right? You can write this as h omega, and I'm going to write it in this way. super n, right? Plus omega sub n times a rank 1 operator, which is delta n, delta n. What is this? Right, you can write it in this way. Okay? And what is omega super n? Of course, omega super n is just a collection of omega n, for n different from n. Okay? And it's of course not the same thing. It's here h tilde, right? The h tilde, right? It's just minus Laplacian plus the potential, where you have set the zero, the nth component here of this diagonal matrix to 0. Right? You just choose to separate. And what happens, the important thing is that these two things are stochastically independent, because your random variables, right, these are independent. Right? Because omega n doesn't appear here, and all the other random variables are independent from omega n by assumption. Okay? And you have a rank 1 decomposition. Right? This is just rank 1, exactly in the same form as before. So this is what makes things work. So the theorem that one gets is the following. So we, theorem, pick phi, well, what I'm going to do is I'm going to take I'm going to rephrase the theorem somewhat. Yeah. It because the way I wrote it here is there's something about h omega. So I'm well, the way I'm going to write this, right? Just to make this clear, I'm going to write this as just h omega n, right? So well. Let's do the following thing. Okay. So pick AB, a compact set in R, right? Then you have the following thing. Then 1 is equivalent to 2, where what is 1, what is 2? 2 is the 1 is the following. One is that for almost every alpha, no, actually, let me think. First, there is something here. Let me think. The way I'm going to state it, I'm going to state it for the operator A before. This is just how I'm going to apply it. But so this, I forgot to say that this is due to Simon and Wolf. I want to change a little bit the statement I've got on my sheet here because okay, yeah, I'm going to make it. I'll change it later on. It's better to change it in the application. So pick in here. Assume. So we look at A pi. Pick A alpha equals A plus alpha phi, right, as above. And assume phi is cyclic for A, right? So what it means the following thing, right? It means that if you look at A and phi, right, and you look at the span of A and phi, this is well, the span of A and phi, right, for all the ends. This is going to be H, right? Then one has the following thing, then one. So same definition as before. To say that G of E is finite for almost every E in AB, right, is going to be equivalent, so 1 and 2, this is equivalent to 2, which is that for almost every alpha, in R, one has, so this is for Lebesgue, right, so almost every here means 2 Lebesgue, just as above. This is also for Lebesgue. One has that A alpha has only pure point spectrum in AB. And the proof goes as follows. As phi is cyclic, well, we know that the spectral measure, of A alpha has the same type as B mu alpha. Right, just because phi is cyclic. And if we look now at set S, it's the set of points of energies in AB, such that G of E is infinite, right? Then assume 1. Then we know that, well, then S has measure 0. Right? But by the spectral averaging, we know that the integral of d mu alpha of S, d alpha, mu alpha of S, d alpha, right, this way. Well, this is equal to the measure of S, that's the spectral averaging, which is 0. Right? But these are positive numbers, right? So it means that mu alpha of S is 0 alpha almost everywhere, right? For almost every alpha. But by the criterion that we have here, what does it mean? It means that S has measure 0, so it cannot be in the AC spectrum, right? It cannot carry any AC spectrum because it has measure 0. But on the other hand, by the criterion that we have, where is it? It's here. It cannot carry any singular continuous spectrum either, right? Why? because we know that the support of the singular continuous spectrum, on the support of the singular continuous spectrum, g of x has to be infinite, right? So the only thing that is left is that S carries pure point spectrum, right? Well, so we get that. So this tells us that mu of L AB, this has to mu alpha, sorry, of L AB has to be 0, right? And so in the same way, of the S alpha intersected with AB has to be 0. Right? These two have to be 0. By the theorem, theorem. Okay. And so the only thing that is left is that mu alpha is pure point. Right? It's carried by the P alpha, what you call P alpha. And the other way around, it goes in the same way, except that you just take the spectral averaging in the reverse direction. So this was 1, so 2 implies 1 now. S is defined in the same way, right? So if we know that mu alpha is pure point, right? Alpha almost everywhere. Then we immediately get that mu alpha of S equals 0. This is by the Organizatор theorem. Right? It's not supported, cannot be supported in this set. And if you integrate the alpha, right, you get that the Bank measure of S is 0. Right? So to follow, yeah, exactly. Okay. So by spectral averaging. Okay, so, and we're going to use this now to prove localization for the Anderson model, as I said. So, theorem. So I'm going to prove first localization, that is the spectral type for the Anderson model. Localization for Anderson model. Theorem. So we consider the Anderson model. We're going to do it, yeah. So we write the Anderson model, so H omega, we're going to take H omega lambda, which is minus Laplacian plus lambda V omega. Lambda will be positive. Right, on L2CD. Then the theorem is that there exists lambda 0 positive such that for lambda larger than lambda 0, H omega lambda has only pure point spectrum. We'll see the exponential, we'll see the exponential decay of the eigenfunctions later, actually, when we're going to deal with dynamical localization. Okay, proof. So, well, let's see what heuristics first. Imagine that we can prove Imagine we can prove proves the following thing. Take the expectation value, right, of the integral from a to b of the sum of delta n h omega minus e inverse delta 0 this squared n. Imagine that you prove that this be finite, right? Imagine we managed to prove. So here I mean, this is of course e minus I 0. Okay? Imagine we assume that one proves this. Okay. Well, then omega almost surely, and e almost surely in AB for the bag. Right? We have the following. We have that h. Oh, sorry, there's lambda missing. Omega lambda minus e minus I 0 minus 1 delta 0 squared. This is just this norm here, right? Inside here, you have this. It's nothing else, right? You just write this vector on the basis. Take the sum of the square of the components, right? And we get that this is this. This will be finite, right? But this you can rewrite as, of course, this is just, so it's h omega lambda minus e minus I 0 inverse delta 0 h omega lambda minus e minus I 0 inverse delta 0, right? So this is h minus e minus I 0 inverse delta 0 is this squared. And this, of course, if you put it on the other side, you see that it is just g of e, right? Where g is for delta 0, right? In the sense that we had before. So this is just, if you want, integral of p mu, the spectral measure for h omega lambda and the vector delta 0, 1 over d e of y e minus y squared. Right? And we know that this is finite. Right? And thus the Simon-Wolf criterion tells us that, well, not exactly the spectral measure for h omega, right, but the spectral measure for h omega restricted to the set generated by delta 0. Because we don't know for the moment, right, that delta 0 is cyclic for h omega, right? But if you have a rank 1 perturbation, you can always restrict it to the set generated, the cyclic set generated by delta 0, right? You still have a rank 1 perturbation of the previous operator A. Okay, and you apply the same theorem. Okay, so what this would show by Simon-Wolf you will know that h omega restricted to the cyclic space generated by delta 0, right, has only pure point spectrum. Right? That's Simon-Wolf. But here, you see, here, when I put delta 0 or not, because I have an expectation, imagine that I put delta k here, put the delta k here instead, then you can get back to delta 0 just using the algorithm. Because if you shift delta k by k, you get delta 0, so you have a tau k here, which means that the tau k goes here on the other side, provided you shift omega, right? But by something which leaves the probability measure invariant. So this shift, because of the expectation, goes away. And you shift this one, but you sum over all n's in ZD, so the shift goes away as well. And so you see that you actually have it for any vector in the standard basis of ZD, of L2 ZD. right? So of course, if the spectrum, if this operator has pure point spectrum on any of these vectors, you have pure point spectrum globally, right? This tells you that you have only pure point spectrum. So if you'd be able to prove this, you'd be fine, right? You'd have pure point spectrum. Well, but this is a bit too strong. This is a bit too strong for the following reason. So, but star cannot be correct. Star cannot be true for the following reason. If I just look at G00, 0, E plus I epsilon, omega. I take this squared. Well, if I take the expectation of this, this is equal to plus infinity. So if you sum, of course, here you have G00 that's a priori, right? So this is just, sorry, this is plus I0. This is plus infinity. As, if you look at F, so how should I write it? If you look at G00, 0, E plus I0, this can be written as F of omega 0 of E plus I0 plus, and you do the perturbation, this is this, and this is, so this is F of E plus I0, 1 plus omega 0 of F of E plus I0. And if you, so I do, here what I mean, exactly what I explained before, right, when I write this one, what I mean is that I take the F, this one, is taken for the random operator, where you have set the random variable at the location 0 to be equal to 0. Right, this is exactly what I wrote in the preamble of my tutorial, which should, I erased it, right here. F of omega 0 is constructed for A equals H tilde omega 0, right? Well, rather than H tilde omega 0 plus omega 0, delta 0, where H tilde omega 0, what is it? It is just minus Laplacian plus V tilde omega 0, and this V tilde of omega 0, omega comma 0, simply omega comma 0, applied to U at n is equal to omega n times U n if n is non-zero and 0 if n equals 1. So just replace the random variable at the site 0 by 0. Right. And you see that this thing here has a pole, right, at the value minus 1 over this. Right, so this certainly, when you take the square, you integrate omega 0, you're going to hit the pole. Right? If you happen to take an omega 0 which is generic, this is going to blow up. Right? When you integrate this against omega 0, so you perform this, because omega 0 sub 0 is independent from omega super 0, right? You can do this by just integrating first in the omega sub 0 variable. Okay, and
there is F squared under the average width is infinity. Average of F squared, not G.
Let me think.
Because F squared.
Oh yeah, you're right. This is F squared. This is G. Yeah, it's just G G. Right? Yeah, you're right. This is F squared. This is F definitely. So the idea, so you see that the problem comes from the fact that you have these poles that cannot be avoided. So the idea is that here what you're requiring is much too strong. If you take, for example, powers that are smaller, right? Here you take powers that are smaller, and you know that the thing is finite, then it will still tell you that and powers that are smaller, and the idea is that when you take this, sorry, you have, so this is, yeah. The square is here. You need to put the square here. Okay. So the idea is to take smaller powers, so to restore integrability, so that you can forget about these poles, these local poles. Right? So the thing goes as follows. So this idea is actually due to Eisenman and Luciano, and appeared first about 20 years ago in a 93 paper. So what we are going to study, the expectation of G n0 e plus I0, but not correct, but to some smaller power smaller than 1. Right, so as to restore some integrability. Right? If you can prove that the sum of these converge, right, then of course it also means that locally these things are finite. Right? Without the power s. If you know that the sum of this converges, then you know that the sum, so the first basic idea is the following thing, it's lemma 1. It's the relationship between what happens when you take powers s, right, and how you relate to power 2. So let s be larger than 1. Then you have that for xn all positive, or not negative, or not negative, you have that the sum of xn over n to the power s is less than the sum of xn over n to the power s. Right? That's what. And now let s belong to 0, 1. Then it goes the other way around. Then you have that xn still the same. The sum n xn to the power s is larger than the sum n xn to the power s. Okay, so let's prove this. So let's start with the first one. So 1, what do I do? So I can assume, so to prove 1, of course if this one is infinite and no problem, right? So I can assume that the sum of xn is equal to 1. Right? I can assume first that the sum is finite, and then I divide by this sum, right? Because they have same degree of homogeneity, I can assume that the sum of the xn is equal to 1, right? Meaning that I take xn divided by sum of xn. If the sum of xn is infinite, anyway that is going to be true, but infinite, possibly infinite here, that's fine. Okay, so I can assume this. And then what I want to prove is that the sum of, so I want the sum of xn to the s divided by 1 over s, to the power 1 over s, sorry, is less than 1. Right, I just need to prove this. Okay. And, well, I'm going to study this as a function of s. Right, I'm going to study this as a function of s. So I put this f of s, and I differentiate f prime of s. If I compute what it is, I get that this is 1 over s. The sum nxn to the s, so I call this f of s, to the power 1 over s minus 1, multiplied by the sum of xn s minus 1 log xn. Right? If I differentiate this with respect to s, I get, and I forgot, no, that's this. This, right? Differentiate in s. You just get the log xn. This one, this one. It's just xn. Right? And this is negative. Okay. So it's decreasing, and well, and then you take s equals 0. Right? And for s equals 0, it's equal to. No, what did I say? Not s equals 0. Take s equal 1, sorry. Not 0. Take s equal 1. For s equal 1, it's 1. Okay? And then for 1 is equal to 1. Okay, so we get the inequality. And the second, in the other case, well, you just set y of n is xn to the s, right? And so what do you have? You have exactly the same inequality, right? So what you want to prove, just do this, right? Set y of n equals xn to the s, and what do you get? You get that this is y of n to the 1 over s. 1 over s is larger than 1. Okay? And you put this one on the other side, you get exactly the power of 2. Okay. So in particular, what this proves what we have is the following, is that if you take the sum over n of g0, 0, e plus i0, right, to the power 1/4, right, this is less than the sum over n of g. Right, we apply the second one, and power s equals 1/4, 0, 0, e plus i0 to the power 1/4. Right? And here, because of this, you see, when you take this to the power 1/4, you get this to the power 1/2, this, of course, to the power 1/2, and the singularity that you had becomes integrable. Okay, so this gets you rid of this singularity. Okay, now the second thing. So that's the first thing that Eisenman Muchadov saw, that you can get rid of this singularity by changing the powers. But because, of course, if we prove that the expectation of this one is finite, right, then we know that what's inside also has finite value almost everywhere. So we'll be fine. And the second thing is that, well, and that's a very clever thing, is that you can actually get some kind of subharmonic estimates for these numbers, right? For these things, you're going to get some subharmonic estimates. But therefore, we'll need what is called the decoupling lemma. Well, yeah, one thing, when I wrote the theorem about the Anderson localization, what did I didn't say? And I erased it already. I didn't. What did I didn't give you any assumptions on the random variables, did I? No. So this, of course, there are assumptions on random variables. Should add this to the theorem, right? Otherwise, we're going to get into trouble. The assumption on random variables assume that. So you just add the following, and I think I gave you the theorem last time already, no? Last time, didn't I give you the statement just before we left? Just check. Yeah, exactly. Exactly. Here. We need to assume, right, that the random variables, in the theorem about Anderson localization, we assume that the omega n's are IID with bounded, it's not really necessary, but it's easier, with bounded, compactly supported density. Right, the admitted density with respect to Lebesgue measure, and it's bounded and compactly supported. Okay? It's not really necessary, but the proof that you're going to give will use this because it makes things easier. Right? But you can do without it. So I forgot to write it. The coupling lemma is the following. So assume let G be the common density of the omega n. Then one has, well, if I compute the integral of 1 divided by, what should I take? X minus beta dg, or g of x dx, g of x dx, divided by the integral of x minus alpha, x minus beta, g of x dx, and I take the supremum of this over alpha, beta in the complex. Forgot, of course, the 1/2, otherwise I'm in trouble. It goes exactly for the same reason as before. So alpha, beta, and complex. Then this I call 1 over C0, and it's finite. And of course, this is positive also. The thing is that it's finite. So, well, let's prove this. So for, it's not very difficult, but so for alpha, so let's assume that let the support of G be contained in minus RR. Right? G. Then if what should I do? What's the easy thing? So the first thing one notice is that if so let me call G alpha beta this function. For this thing, G of H of alpha and beta, right? Because the singularities, because of the square roots here, the singularities at any x are integrable. Right? Because of the square roots here, the singularities are integrable. So this function H is continuous on C2. Right? Just by standard theorems about the Lebesgue measure. Right? Because the things are integrable, just use standard theorems, dominated convergence, for example. Right, and you get continuity. It's continuous on C2. And now, so to get that this thing is bounded, the only thing we need to do is understand what's happening when alpha and beta get large, right? Because anyway, in the compact set, nothing's going to happen. Okay? So we need to understand what's happening when alpha and beta gets large. So what do we have? We have that if beta is larger than 2r, right? Then we know that the integral of 1 square root of x minus beta g of x dx, well, because this is of course, so this is the same thing as integral over minus r, right? We know that this is equal to what? Well, we have that this function here is contained between, so for x 1 over square root of x minus beta is contained in between what? 1 over beta minus square root of beta minus r and 1 square root of beta, sorry, minus beta is 2r, right? So this is contained between 1 over 1, because this is a probability measure. So, right? And in the same way, the other integral of x minus alpha x minus beta g of x dx is, so if alpha I'm going to use the following thing, so I can put 1 over beta minus r, 1 over square root of beta minus r, right? And I have the integral of square root of x minus alpha dg and g. Well, I can assume I can take alpha larger than r. Let's say take 2r again, alpha larger than 2r. So here I can just do the following, same thing, but I have same thing is square root of alpha plus 2r beta minus r and alpha minus r beta plus 2r, right? Okay. And so if I take the quotient, I see that if alpha larger than 2r and beta is larger than 2r, I have that this thing, the h, alpha beta, is less than, well, you take the quotient, this one is below, this is 2, you have 1 over r, square root. Right? So that's fine, that's nicely bounded. Right? Now, if you do the same thing, but you just take alpha in the bounded set, right? Let alpha be bounded, what do you get? You get, so if alpha is less than 2r, and beta is larger than 2r, if you have this, what do I get here? I get that, well, this is going to be bounded. So here, you can, here you need to use one thing, you need to use the extension. So in this case, you know that the only thing you need to say is that the integral of x minus alpha g of x, you use the same thing as here, right? You use the same thing as here, except that you keep, instead you just do the reduction for this one, right? And the one here you keep, right? But we know that g is a continuous function. Sorry, that's a continuous function. G is not supporting the point, right? G is not a Dirac mass. So we know that this is actually lower bounded by what? You just remove, so what you do is the following thing. lower bounded by epsilon, right, times the integral of g of x dx for x minus the real part of alpha larger than epsilon squared. Right? And now if you take epsilon, so now you just look at what's happening to this, okay, to g over this interval, and so you want to prove that this is actually going to be non-vanishing. So what do I need to do? What do I need to do? So I'm looking at integral for x minus, I can take alpha real, x minus alpha larger than epsilon squared, g of x dx, right? Okay, and the only thing I'm saying is that, well, this is 1 minus the integral of x minus alpha from alpha minus epsilon squared to alpha plus epsilon squared g of x dx, right? And this is bounded from above by what? By 2 alpha squared, the sup norm of g, 2 epsilon squared, sorry, the sup norm of g, right? So this is larger than 1 minus 2 sup norm of g. Okay, so if I take epsilon small enough, this is larger than 1/2. If 2 epsilon squared g less than 1/2. Right? And so I get that this is lower bounded by epsilon over 2. Right? So epsilon chosen like that. And the other part, right, if I take the, so I have this, and then if I take this, so I get that if what? If alpha is less than 2r and beta is larger than r, than 2r, I get the following. I get the integral of, I get that h alpha beta is bounded by epsilon over 2 divided by, here I have beta plus 2r, beta minus r, right, square root, and this thing here is, so I have 3 minus, I have 3 epsilon, sorry, it's 2 over epsilon, I have 6 over epsilon, right? So I just do the following thing here, I do the same thing here, but I just use the bounds for this part, for the denominator, right? And for the numerator, I use this bound. Okay, so I get that it is bounded by 6 over epsilon. And then we have the last part, if alpha is larger than 2r, and beta is less than 2r, right? Then what I do, I just use the bound that I have that. Same thing, I again divide. Well, what I do is, I use the bound I have for the numerator, but the denominator stays fixed, right? In this integral, I just use the numerator that I bound, right? But now, if I use numerator that I bound, I get that this is less than alpha, sorry, 1 over alpha minus r. And if I keep the denominator in the integral, I get the same integral as I have above, right? So they just cancel, right? They just cancel one another. I guess this is and I see that the thing is bounded. Okay. When either alpha or beta is large, I get this bound, and when it's on a compact, I just have a continuous function, which is Okay, so I go to C0, 1 over C0. It's okay. So that's the first thing. And the second thing is I'm going to use facts of the So, lemma 2 that I will need is 1. So if you take f and g, two bounded functions on ZD, so f and g that are non-negative, meaning that all the components are non-negative, right? So it's really seen as functions. Then one has 1 plus a Laplacian of f is less than g, implies that f is less than 1 plus a Laplacian inverse of g, right? Where I recall that Laplacian is minus the Laplacian of f at n is minus the sum of fm, m minus n of length 1. Right? And what I mean, if I write f less than g, it means that g minus f is positive. Right? It's not negative. So I first have this, so that if you know something like this, then you have a bound on f. And the second thing is that if for a between 0 and 1 over 2d, well, you have that 1 plus a Laplacian inverse at n minus m. So we look at this matrix and look at its matrix coefficient. This is bounded from above by 1 minus 2dA to the power, the distance separating a and n from m. No, sorry, not 1 minus, it's 2dA, distance separating n from m. 1 minus 2dA inverse. So the kernel here, this kernel decays exponentially as long as a is small enough. So proof of this. So the first thing is just the following. Here I forgot something. Here again I assume this is correct again for a small enough. Forgot to add that. This is for a between 0, same condition as here, and to the inverse. Right? Important. You need this, right? We're going to use it right away. So I know that this norm is 2D exactly, right? Just by the Fourier multiplier. So for a in 0, 1 over 2d, well, we know that 1 plus, so this is 1 plus a Laplacian. Inverse is just 1 minus a minus Laplacian. Inverse is the sum of a minus Laplacian to the power k, k larger than 0. Right? Just do Neumann expansion to compute this result. And this converges, right? Because the norm of this one is a times 2d, and which is supposed to be less than 1. But, well, the one thing is that Laplacian minus Laplacian, by its definition, is, sorry, there's no minus here. Oh, yeah. Put the minus on one of the two sides, all right? the Laplacian is positive preserving, right? If f is positive, minus Laplacian of f is positive, right? So this means that, what do I want? So, if I take h is 1 plus a Laplacian of f, right? Then I have 1, then I have h less than g, and if I compute 1 minus 1 to h, this is less than 1 minus 1 of g, right? Because once you know that if f is positive, Laplacian of minus Laplacian of f is positive, right? Then you know also that for any k, minus Laplacian to the power k of f is positive, right? So indeed, by summing this series, a is positive, you know that the sum of a minus Laplacian to the power k, k larger than 0, of f is going to be positive, right? So we have that this implies this, but this is f, and we get the implication we wanted. And the second thing is actually that comes from the same thing. So that's the proof of 1. The proof of 2 is the same idea. Well, what this shows, the first thing that you note is that minus Laplacian to the power k of n m is 0 if n minus m is larger than k. This comes from the fact that the Laplacian, right, if you look at the matrix, you just have one upper and one lower diagonal. The distance here is 1. Right? You have one upper and one lower diagonal. And so when you compute 1 plus a Laplacian minus 1 at ij or at nm, right? Well, you get that this is the sum for k larger than, so the only place where it starts being non-zero, sorry, this is larger strictly, is when you reach n minus m, right? And you have a minus Laplacian to the power k. Right? But of course, this is at nm. Right? But of course, this is bounded by, well, this operator, a single term is bounded by the norm of the operator. Right? So this is bounded by some k n minus m, norm of the same operator. Right? And well, norm is multiplicative, so we get that this is bound by the sum k larger than n minus m. You know norm of Laplacian 2dA to the power k. Right? And we get that this is less than 2dA n minus m. And then we sum the series from k equals 0, which gives you exactly 1 over 1 minus 2dA. Right? So the crucial fact is this one. Okay, and that's just, you do it inductively. Just reason by induction. So it's true for k equals 1. Okay? And then you do the multiplication and you see that it's true for k equals 2 and inductively. Now the final k. But it really comes from the fact that you have this matrix. When you do the multiplication, the only thing that happens is that you increase the number of sub and super diagonals that are non-zero. If you look at it, another way to look at it is, this is a trigonometric polynomial. If you go to Fourier coefficients, right? You go to Fourier coefficients, this is a trigonometric polynomial of order 1. If you take the kth power, is just a trigonometric polynomial of order k. So it means that coefficients of larger than k, right, because it's larger than k, are vanishing. That's it. Okay, so maybe it's easier, you go to Fourier transform. Okay, you have a trigonometric polynomial, so this is the sum over the cosines of theta j for j being the unit vectors in the lattice, right? And then you take the k's power, you see that you have a trigonometric polynomial of order k, right? And of course, it's meaning that coefficients of order larger than k are vanishing. That's all. Okay, now let's use this to prove the theorem. Back to the theorem. Well, as I said, so pick the non-real, right? And let's look at g of 0n omega z. Right, which is well, there is a, yeah. So this one, yeah, there is a change of notation actually. We know this is okay. There is a change of notation. This is really G00. That's fine actually. That's actually correct. This thing is actually correct because the G of E, the square, right, came from the fact that you summed over these. I take those square and sum. Okay, so this was actually correct. So this is by definition is just h omega minus z inverse at delta n delta 0. Right? Just take this. And we are going to take this to the power 1/2. Okay, as we said before. Okay, and I'm going to define Kn of z is just the expectation of what? It's the expectation of g omega 0 n z 1/2. Just take the expectation of this. Right. Then one has the following lemma. There is the function k of yeah, put the n, and actually stick to my notation. I call this k of n. I forget about the z. I just look at k. It depends on z, of course, but I forget about the z for the moment. Then one has the following thing. One has k of n is less than a constant, which actually can be taken as c0 lambda 1/2 to the minus 1. The sum for the m minus n equal to 1 of k of m plus delta n 0. So you see that this satisfies a kind of subharmonicity condition, right? So this is the Laplacian, and you have k at a point which is less than a constant times the Laplacian at the same point. Except at the point 0 where you have to add zeros. So the proof comes from the eigenvalue equation, actually from the equation satisfied by the kernel. So what we know is that we know that if we take minus Laplacian plus v of omega minus z g omega at z, right? So this is really, if you look at this, this is going to be the identity. Okay? So what does it mean? It means that if you look at the sum over m minus n equal 1 of g omega of m, and here I put n z plus v plus omega n minus z g omega n n z, this is equal to delta of m n, and here, here, what do? I take, so I take this one at m. There's one thing missing here. I should look this at. Sorry. Here I have to think of this is k minus m, right? A sum over k. I take this at k. I take this at, well, no, this is at k. This is at m. This is at m. And this is equal to delta m. Here. Right? So I take the kernel. I fix the second variable. And I look at it as a function of the first variable. And I'll apply the Laplacian to the kernel, then the potential to the same kernel, and I get that it's equal to 0 if the two variables are not the same, and 1 if the two variables are the same. This is the matrix multiplication, right? And you have this one. Okay. I just perform the matrix multiplication of the two operators. So, if I use lemma 1, the first lemma, by lemma 1, I get that if I take the expectation of the sum k minus, well, I'm going to do at 0, so I get m minus m equals 1, g of, how do I call it? I have here, yeah, I'm going to keep the second term. So I keep this term, this second term, so this is omega n minus z inverse, g at omega n 0 z, right, 1/2, 1/2. So I take the 1/2 power of this. So I put this on the other side, I put this one on that side, and I take power 1/2. This is less than delta n0, power 1/2 will not change this. Plus the sum, plus the expectation, sorry, of the sum from, for the m's minus n equal 1 of g omega at m 0, 0, 1/2, right? I just used lemma 1 to get this. Right? And what do I recognize here? This is, of course, this is the sum k, of m minus n equals 1 of k of m. Right? And this one, well, if you remember, what is, so here you have, if now we're going to use the decoupling lemma to deal with this one, what is g omega of n 0 z, right? This is, by definition, delta n h omega minus z. So we can write it as omega n above plus omega n below projector on delta n minus z inverse delta 0. Right? And this I can, using the formula that we had before, right? Remember that we computed this resultant. This is a rank 1 perturbation of that. And we computed this resultant of the rank 1 perturbation explicitly. So this can be written as, so how do I write it? I write it this way, as alpha divided by, so, oh yeah, there's a lambda, sorry, there's lambda here. So we have lambda omega n plus beta, right? Where alpha and beta are complex numbers. Alpha is different from 0, and alpha, beta, they depend on z, they are complex numbers. And so, here I forgot the lambda also, sorry. I need to put the lambdas here. Remember the potential was multiplied by a constant lambda. This is going to play a role. Okay. And so the integral, so what I can do is I can, this expectation, let me call this I is equal to the expectation with respect to omega n, and then the integral with respect to dg, and we keep the variable omega n, so we have lambda omega n minus z to the 1/2 times alpha divided by lambda omega n, or I can put it minus beta here, doesn't change beta, to the 1/2, right? I have alpha modulus to the 1/2, g of omega n d omega n. Okay, so alpha, of course, alpha and beta depend on omega super n. They do not depend on omega little n anymore, but they depend only on z and omega super n, right? And beta, same thing. Okay, that's just one thing. There is one thing I do not understand here. Let me check that. Oh, yeah. So, what I do now, exactly, what I do now, I want to apply what I had before, so I do this divided by lambda, this divided by lambda, right? I get this, and now here in this integral, I can apply the decoupling lemma, right? By decoupling, if I apply the decoupling lemma, I get that this is larger than C0, right, times the expectation in omega n, integral over g omega n, 1 divided by omega n minus beta divided by lambda to the 1/2, alpha to the 1/2, d omega n. Right? Now, I get the same form as before, I put the lambda here, and what comes out is I have a lambda, so I have a lambda to the minus 1/2 coming up. Oh, sorry, lambda to the 1/2. Lambda to the 1/2 coming up. Lambda to the 1/2 coming up. Okay? And what do I recognize here? By this form, this is nothing but integral g omega n. If I put this together, it's just g omega n 0 z to the 1/2 d omega n. Right? So expectation here omega super n. I I get that this is larger than C0 lambda to the 1/2. And here I get Kn of Z. Right? This is just Kn of Z. It's the expectation because I take the expectation first with respect to the nth random variable, then with respect to the other ones. And so I get what I announced. Okay? Well, but this we can also read. This equation here, this equation can also be read as K minus C0 lambda to the 1/2 minus 1 minus Laplacian applied to K, meaning 1 plus C0 lambda to the 1/2 minus 1 applied to the Laplacian applied to K is less than delta 0. This equation is exactly this. Right? This is just written component by component. You have this one here. But this, if you read it as a vector, is just if you take 1 plus C0 lambda to the minus 1/2, C0 lambda to the 1/2 to the minus 1 times Laplacian applied to K is less than the vector delta 0. So we know that by lemma 2, we know that what? We know that K is less than 1 minus C0 lambda to the minus 1/2 Laplacian, plus C0 to the minus 1/2 Laplacian inverse of delta 0. Right? So K, let's say this, which means that Kn of Z is bounded by if, so this is okay, if C0 lambda 1/2 minus 1, so this is minus 1/2 minus C0 minus 1 is times 2D is less than 1. This is less than 1 over 2D. We can apply lemma 2, and we get that Kn of Z is less than, what do we have? We have that C0 lambda 1/2, so 2D divided by C0 lambda 1/2, lambda, to the n, right? And we have 1 minus 2D C0 square lambda to the minus 1. Right? And here, sorry, we have the length. So by lemma 2, we get this. Oh yeah, one thing we need to check that K a priori is in L infinity. Right? We had it for bounded things, but K is in L infinity because it's certainly K satisfies Kn, right, is less than 1 because it's a self-adjoint operator, imaginary part of Z 1/2. Right? This is certainly bounded by the norm of this, and norm of this is bounded by the distance of Z to the imaginary part. So as long as Z is not real, you have this bound, so you can apply the theorem, and then here you get a bound which is independent of Z. Right? So to apply the theorem, we needed the thing to be bounded. Okay? And then now we get actually a bound which is independent of Z. So, then we know the following, right? So we have the following thing now. For C0 lambda to the 1/2 minus 1 2D less than 1, we know that what? we know that the expectation of the sum for n in ZD of G omega 0 n z to the 1/2, right? This is bounded by, well, you can sum this series by a constant, right? By kappa, which is finite. You just sum the series. Kappa depends. It's just take the sum of the series, right? And because this is exponential decay, and so you have a certain. Yes, and of course you can do this for any z. So you have the sup over the z in the complex. This is valid for any z complex, right? For any z, complex, non-real. But you can go to the real axis. You can take the limit. Right? So what you get is that, again by lemma 1, if you take the function g of e before, it depends on omega, right? You have that the expectation of g of e is finite by taking goes to 0. Okay, so g being the sum we had before, right? But you have a power 1/4. This is just by lemma 1, summing the things. That's the first thing we wrote in the very beginning of the proof. Okay, and we can apply the, so we know that the spectrum, so that's Simon Wolf. We know that the mu of h omega, right, on the span, on the cyclic space delta 0, right, this is a pure point. Omega almost surely. Okay? But of course you can replace delta 0 by any other vector. Okay? So almost surely you know it for any delta k in the same, exactly in the same way, just by doing the shift that we spoke of in the beginning. Okay, for any k. And once you know it for any of these vectors, of course, if you look at the space that is spanned by the cyclic space of any of these vectors, it's the complete Hilbert space. So you know that h omega has only pure point spectrum. Okay, this proves the first theorem. Okay. And you see the proof is rather short actually. I mean, it's not difficult. It's not difficult. It uses, of course, a number of arguments, right, that you need some material. But it's not technically difficult. It's astute, right? It's clever to think of this, to see that actually this condition gives you a subharmonistic condition, provided you are able to use it to prove this decoupling lemma, is something clever, right? But it makes the proof very short. If you want to write a proof for the multi-scale analysis, it's much longer than that, right? There are many more things. It's an induction procedure, and there are a number of things to be checked in the induction procedure. It's much more complicated than that. But it is, here the thing is, you don't see anything what's going on. I mean, when you do the induction procedure, what you're doing is you're constructing the resolvent on larger and larger cubes using this induction. And you are actually quite close to the physical intuition behind localization that I explained last time, right? The fact that roughly you are playing to delocalize a vector, you must play exponential decay, meaning tunneling, right, against some probability estimations that is tunneling is occurring, right? But tunneling can only occur because you are in a random medium that can only occur very far away, much further actually than it would be required to get something which changes the nature of your vector, right? Whereas here, don't see anything of that. It's just all integrated, just miraculously, right? Miraculously, turns out to work. One remark is that if now you want to deal with, imagine that here I didn't assume that the random variables have a density, right? Well, for example, if I take something very bad, if I take something like Dirac masses, then spectral averaging doesn't work anymore. And this proof doesn't work. There is nothing, right, like this proof if you take Dirac masses. There is no proof I know of in according to these lines. So this is really restricted to rather nice measures, right? Rather nice distributions. Whereas there are proofs which are relying on more profound facts on partial differential equations for using multi-scale analysis, right? For example, so you see another thing that is very important here, but that was gotten rid of. So it was important in the first version of this analysis, which was actually published in '93. But in 2006, there was a large paper by Eisenman and collaborators where they actually adapted this method to the continuous case. Here we heavily use, to get spectral averaging, we heavily use the fact that you have rank 1 perturbations. Right? If you don't have rank 1, this is not going to be true. I mean, the spectral averaging is not going to work. So this heavily uses rank 1 perturbation. You can extend this to something which is more general than rank 1 in the sense that you still need some positivity and so on, but it is much more involved. Right? It's much more complicated, but it has been done. But one thing I don't think has been done is try to understand how these proofs work if you have singular distributions. Right? If, for example, you take Bernoulli random variables, even if rank 1 it was rank 1. Whereas the multi-scale analysis has been performed and really uses something which is the PDE side to it. You see, if you have, there's one thing. If you take the discrete, so first, there cannot be anything like spectral averaging or Wegener's estimate if you take discrete distributions in the discrete case. Why? Imagine take a Bernoulli distribution. You restrict your operator onto a cube. Okay? Then, because you have only finitely many points in the cube, you have only finitely many realizations of, for Bernoulli variables, you have only finitely many realizations of your random operator. Right? You have n points in the cube, so you have 2 to the n realizations, if it's standard Bernoulli. But it means that the number of spectra that you have is finite. And each of the points in these spectra comes with, so each of you look at the points giving the spectra of the individual random operators, you put these on the real line, and each of these points comes with a certain probability which is positive. So if you take now, if you want to now try to understand what's the probability to have an eigenvalue near this point, right? It's going to be a number which is positive and will certainly not go to 0 if the interval around this point goes to 0. So there's nothing like Wegener, and in the same way, spectral averaging, which is the essence of Wegener, doesn't work either. You don't get that this thing averages out to the Lebesgue measure, right? So this is just, it will not work. But what happens is that, and that's only been proven, so the same thing is the case if you look at the continuous operator, right? Because the continuous operator, each of the you have finitely many realizations, each of them has a discrete spectrum, exactly the same thing happens. But the continuous operator, right? It was possible, this is what actually Bourgain and Klein did, but before them Bourgain, Koenig, and then adapted by the Poisson. This was for the Bernoulli, but for the Poisson case was adapted by Germinet, Hislop, and Klein. And so what they did is they used the fact that even though, well, the spectrum are what they are, you can't do anything, but even what you want to prove, if you want to prove something like spectral averaging or like Wegener's estimate, is that if you wiggle the random parameters, the spectrum is going to change, right? So what we just saw is that you cannot do it to any scale, right? There is a minimal spacing below which you will not be able to prove that the probabilities get smaller when the intervals get smaller. But using PDE ideas, and the basic idea is what is called the unique continuation principle, you know that eigenfunctions for such equations cannot decay too fast in infinity, right? If they cannot decay too fast in infinity, it means that if you change a point far away from where the eigenfunction lives, you nevertheless change the eigenfunction somewhat. You mean changing the point in the sense that you change the value of the random variables. You wiggle the potential. You're going to change this. And you can actually measure this effect, right? And show in this case that there is still something like a Wegener estimate, but up to a certain scale, meaning that it's not going to be true that for any interval of size epsilon around a given point, right, the probability to have an eigenvalue in this interval is going to be bounded from above by the volume of the cube times epsilon. But it's going to be true still for epsilon not too small depending on the volume of the cube. So this is, whereas in this method, this is not enough, right? You don't know, and you can use this actually afterwards to perform the multiscale analysis. So for example, it is proven with using multiscale analysis that you have localization, the same result holds true for Bernoulli random variables or for the Poisson process, right? But not using this method. I don't know of any proof using this method. Okay, so the next time what we're going to do is I'll explain to you how one goes from this to exponential localization. Actually, we're going to prove what is called dynamical localization. So we do two things. We're going to prove that if you look at any function, bounded function of this operator, its kernel has exponentially decaying coefficients of that angle. And from this, we will deduce that if you look at the operator restricted to a cube, right, then the spectrum, of course, is pure point, but you have a characterization of the eigenfunctions. That is, the eigenfunctions will roughly live in small cubes, so you have a big cube. You will show that for all the eigenfunctions associated to an eigenvalue in this cube, the eigenfunction lives in a rather small cube, and of this small cube it decays exponentially. Right? And once we have this, we're going to prove this to prove the spectral statistics. Right? During the last three courses, we'll do spectral statistics using these facts, where we need one more estimate, which is called the Minami estimate, right? Which we'll prove not next time, the time afterwards, so next week. Well, thanks for your attention.